Hello, Assalamu alaikum. I'm Saleh Md Tahsin and my lab mate Shoaib Zawad. Today, we will gonna present our part of the lab 1 demonstration focusing on exercise, addition and subtraction. The goal of this program addition at sub.asm is to perform a sequence of 32-bit arithmetic operations, addition and subtraction, using the EX register as our primary accumulator. We start in the dot data section where we define our single variable total is a 32-bit double word initialized to 0. This is where we will explore the final result. In the dot code main inside main prog, we have our sequence of instructions, each clearly commented to explain the arithmetic steps. So our first step is move EAX 123400 hexadecimal, and then we did a add here, the calculation add 567800 with 123400 hexadecimal. Then we got the result. Uh, this is actually basically comment for showing the result. Then we subtract from this one to this one. And then finally, the final two instructions are very crucial. Move total EX stores 613500H, I mean the result, into our total variable. Then we call dump regs displays the state of all register, which is how we get our output. After this, we show our output. At first, we rebuild and then we debug, start without debugging. Then if we see our output here, we got the EAX 613500, and this confirms the code executed successfully. You can also see the status flags over here. The zero flag is 0, and the carry flag is also 0, and the over flag is also 0, and meaning our 32-bit addition and subtraction did not result in any arithmetic error or overflow. Finally, the message exited with code 0 confirms that the program terminated normally and successfully without any runtime errors. So this program heads2.asm demonstrates how to perform simple 32-bit unsigned arithmetic, specifically addition and subtraction, and store the final result. So let's start with the dot data section. Here we define our variable double words, which means they are 32-bit variable, 32-bit values, and we initialize three variables: value 1 uh, at 10,000 hexadecimal, value 2 40,000, and value 3 is 20,000. Our final variable is final value is where we will store the result. The question mark indicates we will assign its value during execution. So now for the logic in dot code section, specifically within the main procedure, first we use the move instruction to move the value of value 1, which is 10,000 hexadecimal, into the EAX register, will be our primary accumulator for the calculation. Next, we add the value of value 2, 40,000 hexadecimal, to EAX. Now EAX is 10,000 plus 40,000, which is equals to like 50,000 hexadecimal. Then we see the subtraction here. For the subtraction, actually value 3, 20,000, from we subtract it from EAX. The result is now 50,000 minus 20,000, which gives us 30,000. Finally, we move the calculated result from EAX into our memory variable, which is final value. And then the call dump regs instruction is crucial here. It displays the state of the CPU registers, allowing us to verify our result. Let's look the output here. So here you can see we got the result. The EAX register shows the value 30,000. This is the 30,000 hexadecimal, confirming our calculation is correct. And the calculation was successful. And also notice the flags, all the flags, they are showing 0. So that means this calculation is successfully done. In summary, this simple program effectively uses the move, add, and subtraction instruction to perform a multi-step arithmetic operation and verify the correct result which is 30,000 hexadecimal in the EAX register. So this is the program. The goal of this program is to perform basic addition and subtraction on both 16-bit and 8-bit unsigned integers, and then display the results using the numbrex procedure. So first, let's look at our data section. We define their 16-bit word variables, value 1, value 2, and value 3, and their 8-bit byte counterparts, value B1, value B2, and value B3. Our first block perform the 16-bit calculation, value 1 plus value 2 minus value 3, and we move value 1, which is 1000 hexadecimal, into the AX register. Then we add value 2, 4000, making AX equals to 5000. Finally, we subtract value 3, which is 2000. The final result is AX is 3000. Next, we switch to the 8-bit operation, value 1, value B1 plus value B2 minus value B3. So we use a AL register for 8-bit data. Value B1 20 and goes into AL. We add value B2 40, resulting in 60, and then subtracting value B3 leaves the final 8-bit results in AL as 40. Let's run the program. So here the first call of dump break shows the results after the 16-bit operation. Look at the EX register, EX 0019 3000. The AX part, which is 3000 hexadecimal, confirms the first calculation. The second dump break call shows the 8-bit result. Uh, EX is now 00193040. So the AL register, the least significant byte of EAX holds 40H, and then which confirms our 8-bit calculation. The program successfully performed both 16-bit and 8-bit arithmetic, and correctly stored and displayed the results. We see here the flags all are showing 0. That means the calculation is done correctly.
Welcome to the debugging demonstration for part B. The 32-bit operation. We have set our breakpoint and opened the required debugging windows. Here's the watch memory autos registers and the disassembly windows as per the given instruction. So here, I'll press F10 or the step over to execute the first instruction. This moves val1, which is 10,000 H, which is equivalent to 65,536 decimal into the EAX register. Next, we add a value 2, which is 40,000 hexadecimal to EAX. The sum is 50,000 hexadecimal. Here, we can see the sum 50,000 hexadecimal. Finally, we subtract val 3 20,000 hexadecimal from EAX. The final 32-bit result is 30,000 hexadecimal. So here we can see uh, the subtraction value. This instruction stores the result 30,000 hexadecimal into our 32-bit memory variable final val. Uh, Here is the final val. And what's the Windows update? And now the call dump register displays the final state of our register. Here we can see the dump registers. The EX value of 0003 0000 hexadecimal confirms the success of the 32-bit arithmetic. Here we can see the dump bridge. So this completes the step-by-step debugging for part B, demonstrating how the EX register is used to perform 32-bit addition and subtraction. Thank you so much. Assalamu alaikum, I'm Shoaib Zawad and my lab mate is Abu Saleh Md Tahsin. So welcome to part C, the debugging demonstration. I have set a breakpoint and opened the 5 record windows. Watch, memory, autos, registers, and disassembly. Here all the hexadecimal values are perfectly converted to decimal values, which is 1000 hexadecimal values equivalent to 4009 4096 decimal value. So I will press F10 here, step over uh, the first instruction. This loads the value of val1, which is 1000H in AX. In the AX register, and next we add val2 which is 4000H to AX, and see what's the AX update, and now we subtract val3 or 2000H from AX. The final result for the 16-bit operation should be 3000H. So it's 3000H here. And the this instruction stores the result 3000H into the memory variable final val. Final val. Let's look at the watch and memory windows. Here, the watch and the memory windows. The so here the call dump regs displays the current state of registers on the console, confirming our result of 3000H in the AX. See here, AX should show 3000H. Now we begin the now we begin now we begin the 8-bit operations. Here we move val B1, which is 20H, into the AL register. We add val B2 40H to AL. The new value in AL is 60H. Finally, we subtract val B3 20H. The final 8-bit result is AL equals to 40H. We can see it's 40H here, and the result 40H is stored into our 8-bit variable final val B. Note the change in the watch windows. Here we can see the change. This final call displays the registers. We can see 40H in the register, confirming both of our arithmetic results are correct. This completes the step-by-step debugging demonstration. We have successfully tracked register changes, variable storage, and memory updates for both 16-bit and 8-bit operations. Thank you.